we're going to return to the discussion on trees. We'll recall the definition of a tree. We'll discuss the properties of trees, which leads us to a complete characterization of trees. So let's look at this graph that we've seen many times before. It is a tree graph. And let's consider the following. Suppose that we want to remove any edge. Notice that we're saying a tree is a connected graph with no cycles. So I'm thinking about it being connected now. If I remove any edge, what happens to the tree? It doesn't matter which edge in the graph that I remove. Will it remain connected? Let's say we remove edge A. Well, then the vertices 2 and 3 cannot be reached by the remaining vertices 1, 4, 5, and 6. So if I remove edge A, the graph is no longer connected. A was just an arbitrary choice, of course. Any edge in this graph, should I choose to remove it, will result in a graph that is no longer connected. Now, what about the other properties of trees? A tree is a connected graph with no cycles. So instead of removing an edge, suppose now I add an edge. What would happen if we were to add an edge? And again, it does not matter what pair of vertices I pick that are not connected and go ahead and add an edge so that they are now connected by an edge. What will happen to the graph? If I connect the vertices 2 and 4, I'll generate a triangle. If I connect the vertices 3 and 6, I'll generate a path of length 1, 2, 3, 4, 5. And my claim is, what will happen if I add an edge anywhere? I claim that if I add a single edge, I will generate a cycle. So the point is that a tree, in some sense, is critical with respect to its two defining properties. It's connected, but the removal of a single edge will destroy that. And it has no cycles, but the addition of any edge will destroy that property too. So it's right at the critical point where if you add a vertex or edge, if you add an edge or delete an edge, you change its two defining properties. Trees are used extensively in all applications of graph theory. We've seen trees as an underlying structure, and we'll look at that example later in this video. Many computer science applications are algorithms that are defined by a tree structure. Many chemical molecules are tree structures. And in network science, trees play an important role. In our text, we had proposition 3.1.4. Every tree with at least one edge has at least two vertices whose degree equals 1. Now the proof of this is fairly straightforward. Choose a path, let's call it a UV path, a path from U to V, such that it is maximum in length. So over all paths in your graph, there is one of maximum length, at least one, so choose a path of maximum length. Then you will see that U and V must have degree 1 if they're the end vertices of a path of maximum length. If you suppose not, suppose say U has degree 2. Where are its two neighbors? Well, one is on the path, its preceding vertex on the path. If its other neighbor is also on the path, then you'll generate a cycle. And since this is a tree, that can't happen. So its second neighbor must be off the path, but then that contradicts that this is a path of maximum length. So you get a contradiction either way. And hence every tree has at least 2 vertices whose degree equals 1. So this theorem is a characterization of a tree. It says let T be a graph with n vertices, and then the following are equivalent. So what that means is I can pick any 2 of these statements and make an if and only if statement out of those 2. For example, T is a tree if and only if T contains no cycles and has n-1 edges. To prove a theorem like this, you must show that there is a path of implication between any pair of vertices, or pair of statements, So let's look at the 6 statements. 1, T is a tree. 2, T contains no cycles and has n-1 edges. 3, T is connected and has n-1 edges. 4, T is connected and every edge is a cut edge. 5, any 2 vertices are connected by exactly 1 path. And 6, T contains no cycles, and for any new edge E, the graph T plus E has exactly 1 cycle. So any one of these implies the other, and in the implication is in both directions. So this concludes video 1, and we'll continue our discussion on trees in video 2.